So now I'd like to just talk a minute about colligative properties. All right, two major ones I really want to demonstrate: boiling point elevation and freezing point depression. How many people boil pasta? Anybody in here? You boiled pasta before? And do your parents did your mother put salt in the water? Or? And why do they do that? Make it boil faster or something? Why do they do that? It's for flavoring, though, I would imagine, right? It's for flavoring. Yeah.
Elevates the boiling point.
How do you know that?
I just read it.
Wait, doesn't it help like ice and freeze?
No.
We're talking, that's freezing point something, but we're going to talk about that in a second. Yeah, what it does is it elevates the boiling point. Okay, and it has a variety of. Excuse me. I'm going to show you. Thank you. What happens is, here's regular water. Here's regular water, and it's set up for hydrogen bonding in terms of the orientation of the water molecules. Correct. And there's a certain amount of electronics that are there that, Mohammed, thank you for paying attention and staying right with me. I appreciate that. And there's a certain amount of electronics involved that allows evaporation at the surface. Okay. Now you can see that the water is held tightly, and that when it finally boils, you're breaking down the hydrogen bonding to a great degree, not a complete degree, but to a great degree, and you're allowing this rapid kind of vaporization of the water at 100 degrees Celsius. It creates a certain vapor pressure, correct? So that vapor pressure is going to equal the atmospheric pressure, let's say at sea level, and it's going to boil. And we know that at 1 atmosphere, it's going to boil at 100 degrees Celsius. Make sense? Yes?
Wouldn't salt be kind of like a catalyst?
No, not yet. Let's think about it for a second. Is sodium chloride more or less electronic than the electronics behind hydrogen bonding? More, much more. There's a lot of electronic forces involved in the ionization of water. You have all of these positive and negatives in, for instance, sodium and chlorine, correct? So you get this sodium chlorine solvation process where it's like almost like a magnet is the salt molecule, and if you put it in iron filings, you have the iron filings just adhere to the magnet. Well, the same thing could be true in a solution where you have these rather large ions that are positive or negative, and then you have the water that is not ionic, it's just polar, and those water molecules are going to cling to the ions like iron filings on a magnet, where the magnet is the sodium or chlorine and the iron filings are the water molecules. So are you going to have as many water molecules able to escape from solution? Are they going to be more easily, are the water molecules more easily going to escape from here, from A, or from B? Where are the water molecules more easily going to escape from, A or B? Why B, Aaron? Why B? You see, hydrogen bonding is creating, see, water by itself should have a high vapor pressure. Remember we talked about that? Meaning water molecules should be able to escape quite freely, correct? But they don't. Water is a very bizarre substance, right? Didn't we talk about that in chapter 13? Remember, we talked about that. And we talked about that when we talked about water and aqueous systems. On paper, this should be a very volatile collection of particles, but it's not because of the hydrogen bonding. So the hydrogen bonding keeps that vapor pressure low. It's going to boil at 100 degrees, not at 80 degrees like alcohol would, or at 60 degrees like maybe an ether, one of the ethers would. It's going to, you have to heat it. You know, you have to heat it to 100 degrees in order for it to get enough vapor pressure. It has a relatively low vapor pressure, doesn't it? Okay. What keeps it at that vapor pressure? What keeps it there? What keeps it at a low vapor pressure? You can do this. I'm losing them. Hydrogen bonding, right? Now, I take hydrogen bonding, and I just said that hydrogen bonding is relatively weak relative to the ionic bonding and the electronic forces involved in ions, correct? Correct. So now I'm going to put ions in here. Is that going to make this more electronic and harder for the water molecules to escape, or easier?
Easier.
You're still not getting it. You're not getting it.
No. It just clicked right now.
What does just click? The fact that it's 50-50?
No, that's not it. Sorry.
Okay, so which one will be harder to boil?
B.
A or B?
B.
Why?
It has more.
Greater electronic forces prevents the escape of the water molecule, quite simply. Do you understand that? Do you see that?
Yes.
Are you sure?
Yes.
Don't say that because I'm telling you that. Do you see it? Okay. Well, we have a way of quantifying this. We have a way of quantifying it. We have a way of calculating precisely what the elevation in the boiling point will be. Can we determine the actual boiling point of a solution of water and sodium chloride? Can we determine it? Let's see if we can do that, okay? We'll come on to the next. This is introduction to freezing point depression. Boiling point elevation. And then the next film will be a problem on boiling point elevation. Clear? Okay, good. And then we're done. Understood for the day. Clear?
Are you going to do another one for freezing point?
Yes, I'm going to do another whole thing. 2 films for freezing point, but not today. Okay.